Second video, metapopulation models. So what I want to do here is to give you some idea about a method that can be used to model space, and we will see that method used in a variety of models of foot and mouth disease and avian influenza in the next video. Um, it will not be the only type of models that are used here, but I thought, okay, this is something that I believe is an interesting topic that you may want to apply yourself, and therefore I'm going to explain how things work. Um, First of all, I'll mention two types of metapopulations, and you will see what I mean. And metapopulations operate in graphs, and so I'll talk about the graphs, what I call a generic model, talk about the analysis of those models, computation of the reproduction number, for instance, and then I'll say a few words about the numerical simulation of that type of models. Ah, oh, this is not where I need to be. So, first question, essentially, what is a metapopulation? So a metapopulation is a population of populations, hence the meta. There's two types of metapopulation models, and this is what I'm going to go over soon. First type is what I'll call a patch occupancy model, or in the terminology that you just saw in the table of contents earlier, this is a metapopulation à la Levin. Sorry, patch occupancy, this is à la Levin's, whereas a model with explicit movement is a model à la Levin. Okay, we'll come back to that. The idea, what separates these two types of models is that in one, we're essentially concerned with whether a location holds a certain species. There are sort of distinctions there. That's not the only types, but a patch occupancy model is essentially, and you will see some of those models later when we look at whether farms are infected or not. So this is what I'll call a patch occupancy model, or a metapopulation with implicit movement. That's actually not exactly synonymous with patch occupancy, but we'll come back to it. The idea being, as I say, that really what's important is whether the location is infected or whether it is it hosts a certain species or so on. And then there's models with explicit movement. And in that case, what happens is that we look at locations and we consider the possibility for individuals to, well, not only the possibility, but we allow individuals to move between locations. Okay. And so what happens is in there, we explicitly move individuals between locations. And I'll point out both types of models have their advantages and drawbacks. I typically have worked mostly with explicit movement, and this is what I will detail here. But as I said in the foot and mouth examples, for instance, we'll see what are more patch occupancy models, and you'll see that they also have good properties. Now, the underlying idea to a metapopulation is that essentially there's a bunch of locations, which when we think as mathematicians more than ecology people, uh, we think of locations as being a geographical place. You will see metapopulations used in a more ecological point of view, but in that case, the definition of a patch, what they call a patch, is a bit different from the one we use here. Here, I'm going to think, you can see this underlying map that I have here. This is a map that is segmented in terms of the airports. And this could be a location. Okay, a location would be even catchment area of the airports that you can see in this map here, for instance. But very easily, we could also consider a location to be a city, a region, a country, a farm, as we will see in the foot and mouth disease problems, or in some of the avian influenza ones. You can be more or less relaxed about what you call location. There are some instances where locations will overlap, but I'm not going to go into details here. Now, the first type of model that I want to look at is what I call here metapopulations à la Levin's. So this is Richard Levin's, and the paper that I'm talking about is a paper from 1969. And this is an ecological point of view paper. It's not a paper about diseases in particular. It is a paper about the distribution of species. It's quite an influential paper. It's been cited quite a lot of times, and it's got also quite a number of second and third generation offspring. Okay. Quickly, this became very used a lot for predator-prey or competition systems, but it's seen a variety of applications. So, and this is where you'll see that this is very similar to some of the foot and mouth disease models that we will see. Here, the idea is that he considers the rate of change of the number of local populations. So P of T is how many local populations there are. Local populations being, okay, there's well, okay, let's think about farms, go back to the foot and mouth disease problem. This would be the number of infected farms, for instance. And so here they're looking at, so he's looking not at a disease, as I said, but so he's looking at an immigration rate. So this is a logistic equation, essentially, okay, minus term. This could be a harvesting equation, for instance. So P is the number of locations with the number of local populations. Beta is an immigration rate between locations. T is how many locations there are in total. And mu is a rate of extinction of local populations. Okay. Now, if I'm thinking about using this in a sort of spatialized context, what I'm going to do is do something like this. I'm going to consider a set of locations that I call locations. And in each location, I'm going to define some internal dynamics. This is a prime. It should be prime. I will correct the slides. So there's an internal dynamics. This is a differential equation. X prime of t is equal to some function that is dependent on the location as well, times, well, of evaluated at the state of the location. Okay, so xp is some state variable that has dimension np, and fp is a function that describes the evolution of that equation. Typically, when you have implicit movement, so something a la Levin's, you have no flow of individuals between locations. Okay, so you're just assuming that there is an influence of the other locations onto the location of reference. So if I'm thinking about location P, I'm saying there is an influence of individuals in other locations whose numbers are xq, and this is the influence uh, of q on p. Okay. So if I want to describe the dynamics of that system, then I have something like so. Here I have a derivative. Good. X prime, so the evolution, the rate of change of xp is given by this internal dynamics, okay, plus this function that describes how the other locations influence location p. Okay. That's a model with implicit movement. Now we switch. So the previous model was Richard Levin's. The type of model here is Simon Levin. So this is a paper of Levin in 74. So I remind you that this is what we're looking at in a Levin's type model, but in a Levin type model, so a metapopulation with explicit movement, we incorporate the movement of individuals between locations. And the reason we may want to do this is that instead of assuming that we have some information about um, the influence of a location on another one, we have explicit movement information. We know that so many animals, if you go back to the example of foot and mouth disease, you can think of these flows of animals that we saw between the different farms. If we have that information, we may want to incorporate that information. Okay, so in that case, we have explicit movement. So same as before, we split space into a certain number of locations, and I'll point out that they're often called patches. Okay? You will see some of those models called patchy models or patchiness, etc. But as I said, I prefer to use the name location because it's really a geographic location that I'm thinking of. And each location, it can contain compartments in the sense of compartmental models. Okay? So it could be prey and predators, it could be infected and susceptible individuals, etc. And so just to illustrate what happens, I'm going to suppose that I have a single compartment in each place, uh, whatever species I'm interested in. Okay? And I don't consider anything else. We'll come back to disease situations later. But for now, just let me explain using this. What's going to be important is I'm going to use a rate of movement from location P to location Q. Okay. Um, so you can, I'll mention it again, but you can see that the index is from to Okay, sorry, to from. So Q is where I'm going, P is where I'm coming from. And that rate is going to be a non-negative value, okay? It just says, well, if it's zero, there's no movement possible from P to Q. And if it's positive, then there is a rate of movement of individuals from P to Q. And so what we have is something like this. So here I'm illustrating the situation that would prevail if I'm looking at the population in location 1, where I'm going to write P1. So P1 of T is the number of individuals present in location 1 at time T. The way that number is going to change is influenced positively by those red arrows. So the red arrows are the movement from a given location, 6, 5, 4, etc., to location 1. Okay, this is the rate of movement from 6 to 1, from, so there's none here, from 4 to 1, and so on and so forth. And these movements influence positively the number of individuals in population 1 because the individuals who are coming from the other locations are increasing the population in one. And likewise, I mean, the other way around, if I follow the blue arrows, I am leaving location one and going to the other locations to which it is connected. And the rate at which this happens is simply the sum of the weight, the rates along all the arrows. Okay, so the way population one changes, the population in location one changes. So P1 prime of T, okay, the derivative of P1, is positively influenced by the terms in red and negatively influenced by the terms in blue. And I'm going to point out right away a little trick, which is to write that M11. You can see that here. So if you think about it, I have no rate of movement from 1 to 1 because I am in location 1. I don't need to travel to location 1. But, and so when you look at the sums here, they exclude 1. But I can play this little trick here where I say that the rate of movement from 1 to 1 is simply the negative of the rates of movement from 1 to all the other locations. And when I do so, instead of two equations here, I get a single equation. Okay. So this equation here is exactly equivalent to this one, provided that I write that M11. So notice here I am not excluding any j. So when j is 1, I have M11 here, and M11 is minus this term. And then when j is not 1, I have the same thing as I have here. Okay, so M11 is the blue term here, and the others are the red terms. And that's going to allow me to write the dynamics very simply. Now, how do we analyze that? Well, the first thing we need to do is to sort of set up the system. So the system is a graph. I mean, here you see you have a mathematical graph where the vertices are the locations and the arcs are, so this is a directed graph, okay? The arcs represent the possibility for an individual to move from, for example, 6 to 1. So the setting that we're going to work in is one where we have a set of locations P. If we write that symbol here means cardinal, so number of elements in that set P. And those locations, they're the vertices of a directed graph. Each location may contain a certain number of compartments. So the analogy that I'm going to use throughout is that of an SIS model. I mean, I'll use a more elaborate model in a while, but for now, think about an SIS model. So each location, if I had an SIS metapopulation epidemic model, epidemiological model, every location contains an S and an I. Okay, so this is that set, it's the set of compartments. And the arcs in my graph represent the possibility for a given compartment to move from one place to another. So if I have, for example, a model that has S and I as compartments, so an SIS model or an SI model, then the S and the I can move. That means that between any two locations, I can have two edges. Okay. And I'll point out that this is a digraph. The movement is not always symmetric. And I mean, if you think about it, there's a rate of movement. And so the arrows might exist in both directions, but the weight of the arrows is not going to be the same typically. So what we have is a multi-digraph, as I said, with a set of vertices that are the locations, a set of arcs, and these arcs are what we call an ordered multiset of pairs of elements, okay, because they represent all the possible arrows for each type of compartment. Okay, so what we have in practice is what's called a multi-digraph. What here is a multi-digraph, but if you think about the details for each compartment, so for the S and for the I, we have a digraph that represents how compartments S and compartment I can move from one location to another. From that, we deduce what is typically we would call an adjacency matrix, but I'll call it connection matrix here because I'm really thinking about the location to location connection. Okay, so, but it's an adjacency matrix. If you've done graph theory, you know a connection, sorry, an adjacency matrix. This is an adjacency matrix. Just giving a slightly different name. And we can let's skip over this particular details. It's just to make things tidy mathematically. Essentially, what this is saying is that when you're looking at a collection of locations, you typically think of all the locations as having the same index. So if location 1 for the S is the same as location 1 for the I, for example. Typically, often what we'll use is the name of locations. So if I'm thinking about the movement of animals between farms, I'd say a farm in Winnipeg and a farm in Brandon, for example. I will use two names. So that's why. One thing that is really important here is the notion of strong connectedness. So we say that if you think about a given compartment, I should say C, but a given compartment S, what we call the strong components of the graph, the corresponding graph, are the set of locations where you have access from any location to any other location. Okay. And so sometimes you have subsets where, for instance, if you think about, okay, think about the set of locations that are accessible to you with your passport, for example. Well, typically all the locations in one country will be accessible to you, or they won't. So you could think about it that way. And then strong connectedness altogether is just the property that if I have a set of locations and any two locations can be reached, there's a way of going, and it's not necessarily direct, but any location can go to any other location in a finite number of steps. Then this is strong connectedness. Why is this important? Is because there's a strong link with matrix properties. So we say that a matrix is reducible. So now I'm switching to matrices, but you will see that this entire theory relies a lot on the link between matrices and graphs. Okay. So a matrix is reducible if there is a permutation matrix, so a reordering of the rows and columns, that is such that what you have is a block upper triangular matrix. Okay, so you have a matrix which has a block of zeros below the main diagonal, somewhere, below the main block diagonal. And a matrix is irreducible if it is not reducible. Now, characterizing a reducible or irreducible matrix is not necessarily easy, but this is why there is this strong link between the graph theoretic aspects and the matrix aspects, is that there is this theorem, I'm not going to show, okay, this is not the purpose here, but there is this theorem that tells you that your graph being strongly connected is equivalent to the irreducibility of your connection matrix. So you can look at a set of locations as a graph and try to ascertain whether you can go from any location in that graph to any other location in that graph. And if that is true, then you know that the matrix that corresponds to that graph is irreducible. Okay, so this is sort of the preliminaries that we need. Let me show you a little bit how you analyze this type of model. What I'm going to do is I'm going to denote NCP of t, but I'm going to drop the dependence on time if I don't need it, which I typically don't. But remember that state variable depend on time. And I'm going to denote NCP of t, the number of individuals who are in compartment C in location P at time t. Okay, so if you think about how to represent this, there are two ways to do so. There's one which is to look at the distribution of individuals of a given compartment among the different locations. Okay, so this will be that vector, and this is what we will be using most of the time. So this, let's go back to the example of an SIS model that I was talking about before. When I write my metapopulation model, SIS model, what I'm going to have is I'm going to have the number of susceptible individuals in location 1, number of infected individuals in location 1, number of susceptible individuals in location 2, number of susceptible infected individuals in location 2, and so on and so forth. This vector here, for example, I would consider S. And I would say that vector S is the number of susceptibles in location 1, 2, 3, etc. Whereas this notation, that I'm going to use very, very rarely, is the composition of the location. So if I have an SIS model, in each location, I will have some susceptible and some infectious. Okay, and so this is for each location, how many susceptibles and infectious there are. As I said, we'll use mostly this notation. And this may look a little abstract for now, but we'll be looking at examples very soon. Okay. Now, if I want to go up from the model I was using before, if you remember that simple example where I had just the population in 1, population in 2, here I'm going to look at the same type of thing, but I'm going to allow the number of the compartments to change as well. So this, first of all, I'm going to use linear autonomous movement. I'm not going to explain essentially what that means. Is simply that this M here does not depend on time, and it doesn't depend also on the numbers. I mean, it's a linear function of the numbers. It is not a non-linear function of the numbers. So if I'm looking at a given compartment C and a given location P, the evolution of the number of individuals in compartment C in location P is given by, and this is the same thing we saw a bit before, this is the dynamics of the number of the number of individuals. Okay, how the individuals present in the location influence the change in the number of individuals in compartment C in that location. Okay, so this depends on the individuals that are present locally, and only those that are present locally. Okay. And then these two terms here are the movement terms we saw before, but I've added one index here because I'm not just looking at the number of individuals in location P, I'm looking at the number of individuals in compartment C in location P. Okay, so I've added one index to my rate of movement, you can see here, my first index is the number of individual of the compartment that I'm looking at, which is the same as this one. And then it's the rate of movement from location Q into location P, okay, times the number of individuals in location Q that are, of course, in the same compartment, minus those that leave location P, and of course, that are of compartment C. Okay, so you can guess what we are going to do. The next step is going to be to simplify that same simplification I introduced earlier. I'm going to introduce it here. So remember that there's one extra index here, but it doesn't make any difference apart from this. I'm just saying that the rate of movement for individuals of compartment C between P and P is simply the negative component of this. So this guy here, I move here, and when I do so, I end up with this very simple equation, which simply is, oh, this is not NS, it should be NCP. NCP prime is simply this plus this movement term, where the movement term includes the flow out as the movement from P to P. Now, if I want to write this as a vector, and I will need for the analysis, then I have something like this. For each compartment, C, my distribution, my vector that describes how the members of that compartment are spread out between the different locations is some function of the internal state. This should be NP, okay? But this is a vector function here, okay? So that's why it's just n, plus what I'm going to call the movement matrix times the vector nc. And the movement matrix is this matrix here that is extremely important in all those metapopulation models, that simply has as diagonal terms those negative sums that I've defined. Okay, if you remember that negative sum here, these are what ends up being on the diagonal. And on the off diagonals, I have the rate of movement for compartment C from, for example, 2 to 1, 3 to 1, etc. This is by row. Okay, so this is a very compact notation that is going to be extremely useful in trying to understand what those models do. And as I said, the most important component essentially here is this movement matrix. That movement matrix is where all the information about movement between your locations is encoded. Here are a few definitions that I would be using. So I'll denote R to the power n cross n, the set of real square matrices. Okay, and the entries in the matrix are of course always denoted Mij, where I is the row and j is the column. We say that a matrix is non-negative. So this changes a little bit. My notation is like this. I'll write that m is greater than or equal to 0 if m is the entries are greater than or equal to 0, but that includes potentially the 0 matrix. I'll write that m is greater than 0 like this if it is non-negative and that at least one entry is positive. Often you will see that notation here used for what I denote this, but I like to make things very clear. So this for me can be the 0 matrix. This cannot, okay, because I'm assuming that there's at least one entry that's positive. And if all entries are positive, what we call a positive matrix, I'll denote that way, okay? And the same notation, of course, is used for vectors. I'll denote sigma the spectrum of the matrix. That's the set of all the eigenvalues of the matrix. Rho is the spectral radius, which is the maximum of the moduli of the eigenvalues. S of m is going to be the spectral abscissa or spectral modulus, and that is the maximum of the real parts of the eigenvalues. And finally, something we'll use quite a lot, we'll say that M is an M matrix, but a matrix is an M matrix. If it is a Z matrix, that's a matrix that has non-positive off-diagonal entries. Don't care about the diagonal, okay, but it's non-positive on the off-diagonal, and it can be written as S times identity matrix minus A, where A is a non-negative matrix and S is larger than the spectral radius. And I'm not going to show you how this comes up, but this is a very cool property for a matrix to have. Okay, we're not going to look at the characterization, but it is a cool property and it's really useful. Now that matrix that I called movement matrix earlier, it is very, very important. Okay, and pay attention to the fact that it describes both the existence of a connection. So if an entry is non-zero, this means there is a connection. But when an entry is non-zero, this is also the intensity of the connection, okay, the rate of movement from one location to another. A few remarks about the matrix. It's what's called minus its value is what's called the Laplacian matrix of a graph. So there's a lot of properties that are known for Laplacian matrices, and so knowing this is useful. Zero is an eigenvalue. Okay, when I write something like this, I mean zero is an eigenvalue, and it corresponds to the left eigenvector that just consists of ones. So this is a row vector with just ones, and that row vector is an eigenvector corresponding to the eigenvalue 0. Minus m is a singular M matrix. Okay, M matrices are useful, but you'll see why soon. Also, 0 is not only an eigenvalue, but it's also the spectral abscissa of the matrix. That means, remember that the spectral abscissa is the maximum of the real parts of the eigenvalues. So what this means is that all eigenvalues are non-positive. All eigenvalues of M are left of the imaginary axis or on them. I mean, 0 is on there. So all eigenvalues are left of the imaginary axis. There's a paper of mine with Nicolas Bajeux and Steve Kirkland from a couple of years back, where all these results are proved as well as those. And we're going to use this first result a lot, and a few of the other results a little bit. So the first result is what you could call a spectrum shift. Okay, so this says that the spectral abscissa, when you shift, so remember that M is a matrix that it's not invertible, it's a singular matrix because it's got the eigenvalue 0, but when I shift its spectrum, well, if I add d times identity to the matrix, then the entire spectrum is just shifted right by d. And you can also see that the spectral abscissa, if I shift things by using a matrix D, diagonal matrix D, that new shift, again, but this is a shift that can have different values, okay? This is a shift of a constant where I'm just adding D times the identity, but here if I add a matrix D, well, my new matrix M plus D has a spectral abscissa, an eigenvalue. Okay, what's going to be important later is this one. For instance, if I add a diagonal matrix where all the entries on the diagonal are positive, uh, then I have an invertible M matrix, and that M matrix inverts to something that is positive. And if on top of that, well, I mean, not on top of it, it's not exactly the same. If instead M is irreducible, so remember this means that any location has access to any other location, not necessarily directly, but there is a path from any location into any other location, and that my diagonal matrix that I perturb with is uh, not all zero, then D minus M is a non-singular reducible M matrix, and it's entry-wise positive. Its inverse is entry-wise positive. And we'll see a couple of applications of that. I'm not going to spend a lot of time on the math, okay, but I just want to give you the operating principles and sort of show you that you can manipulate these objects uh, quite easily. Now, let's look at the behavior of this type of system a bit. The first thing that I can look at is what happens if I just have I have no internal dynamics. So I'm forgetting the idea that I might have an epidemic model. I'm just looking at the evolution of the system with just the movement matrix. Well, in that case, what we find is that the total population, not the total, the distribution of population in each location for compartment C actually goes to a positive value. Okay? And that positive value depends on how many individuals you had at the beginning. Okay, because this is simply saying I can mix things. So imagine a model where I have all my susceptibles and I don't assume that there is any dynamics. So I just have, for example, my susceptibles and my infectious, but I don't assume that they mix. They're just equally spread in space, or they're spread in space. If the movement matrix is irreducible, that means if any location can eventually reach any other location, then what's going to happen is that the individuals are going to spread in the locations uh, based on a variety of factors, but all of the individuals, I'm not assuming there's any birth or death, okay? Then all the individuals are just going to allocate themselves in space. And that's useful to know, because what we are going to do quite a lot of times is to actually look at the total population per location. So I can go from a model where I have susceptibles, infectious, and they're interacting, but under certain conditions, the total population in each location is going to behave well. So if I introduce TP to be just the sum of all the different types of individuals who are there. So remember, susceptible, infected, for instance, then TP here would be just S plus I in each location. Well, what's going to happen is a lot of times that dynamics here, the internal dynamics, is going to simplify quite a lot, and it's going to disappear to such an extent that in the end we have either something like this or something like this plus a constant. Okay? So before you do that, you end up with this sum here, okay, which is going to be annoying, and this dynamics of the population in each patch, each location, that I'll just write as dp of. Now, what happens most of the time, most of the models you will see, is that you will get something like this. Okay, so the dynamics, the internal dynamics, is either going to take the form of B minus D times N, t, okay? Or it's going to be bp minus dp times t. This is something where the population will either go to zero in a location if b is smaller than d, or the population will explode if b is larger than d. A case that you will see very often is the case where you have a D and a B, so the total population is constant. This one, the total population is asymptotically constant. This one is constant. Or you'll see some typically a bit more elaborate models which will have logistic demography. So you'd have something like this. Unique location. When I look at the total population present in the location, I get something like this. The examples I'll show you later, they work with something like so. So when actually look, this is what I'm saying here, and typically I'm going to assume that what I have is something like this. Well, if I do, then I can simplify things this way. So in vector form, the distribution of the total population in each location is going to be governed by this equation. So B is a vector that has the birth rates in each location. D is a diagonal matrix that has the death rate on the main diagonal. It has the death rate in each location. And this is a term that's annoying, okay? Because this is simply saying how the different compartments are moving between the locations. Okay, so I wish to have T, the total population in each location, but when I do that, so that would mean, for example, N, if I write N to be the sum of S and I would have N equals B minus dn, that's the component that I control well, but I would also have a term of movement here that would include the sum of the movement for the S individual and the movement for the I individuals. Okay. So each matrix involved is a matrix of the type that we saw before, but that term is really annoying. Now, what can happen, what's easy, is when I suppose that the movement rates are equal for all compartments. So what does that mean? That means, for example, susceptibles travel at the same rate as infectious. Okay. If I do so, then all my NCs, whatever C is, they all break down to the same matrix, and that means that this sum that I have here, I can pull out the M, and when I do so, remember that this is the sum of all the compartments in the different locations, and so that's nothing but T. So when the movement is equal for all compartments, the dynamics of the total number of individuals in each location, T, okay, so T prime is just B, a vector, minus a matrix times a vector, so a vector, plus this matrix times vector, which is again a vector. And not only is it well described that way, it's also very simple to study. So first thing that you do when you're looking at a system of differential equations, typically one of the first things you do is look for equilibrium. Well, I'm going to have an equilibrium if t prime is equal to 0. Okay, 0 is the 0 vector here. So I have a vector with cardinal of p locations, and I'm saying, well, I have an equilibrium if that vector equals the 0 vector, which I write using my equations, and you can see that I can factor out here. I can write, I can move the b, well, I can move these two terms on the right hand side, and so I get b equals d minus m times t. So if d minus m is invertible, I then have that my equilibrium is going to be t star equals the inverse of d minus m times the vector b. Okay, I just need to invert this thing. I multiply both sides by the inverse of d minus m, so I get inverse d minus m times d minus m, which is identity, times t, so t equals inverse d minus m times b. This is what I have here. But of course, what I need is for this matrix here to be inverted. I need to be able to carry out this operation. And that's where all these properties we saw about the movement matrix M are going to prove useful. So one way to think about it is, okay, so can I invert this matrix? I don't remember. Here I have it as d minus m, but of course, if I can invert one way, if I can invert m, I can invert minus m. Okay, so here this is simply, instead of looking at d minus m, I'm looking at m minus d. So I take this spectrum shift theorem that I saw before and recall that the spectral abscissa of M is 0. All my eigenvalues are either at the imaginary axis or left of them. So what happens when I subtract the smallest of the diagonal entries, okay, for def rates? Well, I shift everything by this quantity. And so if I assume that all def rates are positive, which is a very reasonable assumption, you can assume they're, I mean, in the worst case, you can assume they're very small. But if I assume that all def rates are positive, then I know that all my eigenvalues are left of the imaginary axis. All my, so I have no zero eigenvalue anymore, so the matrix is invertible. Okay, so that means d minus m inverse exists, and I can compute this. I could also, if you remember, we saw that if your matrix is irreducible, then you have similar property. Well, you can invert it. So I could also assume that the movement matrix is irreducible, and in that case, that's also going to work. Okay. Then I need to know that this equilibrium attracts the solutions. And remember that the equation is this nice linear equation. There's no nonlinearity here. So it's quite easy to decide on whether T star attracts all solutions. So I'm just going to write the solution of the differential equation this way. So as f of capital T. And when I look at the derivative, so the Jacobian, okay, of this f here, I get n minus d. And I've just seen that f and n minus d is invertible, provided all the d's are positive or that the m is irreducible. Okay, so in both cases, I'll get that this is, sorry, this has s of this negative, so all the eigenvalues have negative real part. Because they all have negative real parts, but solutions all converge to T star. Because this is linear, okay? It's a linear system. Okay, so now this is the sort of general theory. Let me show you a few examples because I think it's much easier to understand if you see examples. So the thing that I'm going to use as a toy system is the following. So this is an SLIRS model. Here I've taken a model that is has birth that is constant. The death is per capita. Okay, it's multiplied by the density in each of the compartments. You can see that there's also disease-induced death here. There's out of the I compartment, There's a d plus delta I. I'm not sure I use it everywhere, but never mind, it's easy to do with or without. And loss of immunity happens at the rate nu r. So this is a very classic SLIR model, SLIRS, okay, because there's a loss of immunity. The force of infection is going to be something like this, and I'm actually going to take it either proportional or mass action, so much simpler. Phi is just going to be beta Si over n or beta Si, depending on the cases. So what does that look like in a metapopulation model? Well, it's very, very simple. So all you need to do, this is the simplest possible metapopulation derived from that model. It's what I'll call a cardinal of P SLIRS model. You can see that I have a single index here. That index tells you what location you're in. So P is in that set P of locations. And you can see that I have constant birth, death here. So if you focus on the terms in white, this is exactly the same as this. And I don't have disease-induced death. Okay, I should remove a disease-induced death here. So you can see that these terms in white, they're exactly the same as those in the single population model, single location model. Except that I've added an index because I can say, well, this is location 1, location 2, or location Winnipeg and location Toronto, whichever way you want to think about it. But I have these terms in red, and these terms in red represent a movement between the locations. Okay. So this is a very simple way of looking at things. And you can see, by the way, here my first index is the compartment. So you can see that I can have, I'm not necessarily thinking they're different, but I can have different movement rates for the susceptible individual, latent, infectious, and recovered. Okay. The infection term is simply the product beta P, number of susceptible in P, times infected in P, divided by the total population in P, so in location P. And I'm using this to allow two different cases. You see this value, QP, if I take it equal to 0, then this term is equal to 1, and I'll have a mass action type infection term. And if I take it equal to 1, then this is beta PSPIP over NP, which is a standard incidence. Okay, so by playing with QP here, I can make each patch, each location have potentially different incidence functions. Okay. I can set a model like that. Okay. Now, I can make things more complicated. So this is what I'll call an cardinal of PSLIRS model. And in short, what it is it's a multiple species model. So that set S represents the species. So I have my locations like before, but additionally, in each location, I have species. And so you can see that now instead of one index, I have two indices. The first one is for the species, and the second one is for the location. So in each location, and for each species, I have exactly the model that I had before. Okay. Plus the movement terms as before, and you can see that the movement terms here I've had to add one extra index again, because I'm looking at the movement of individuals from all locations from, so this is the movement of individuals from species little s who are susceptible, okay, from Q to P. So susceptible from Q to susceptible from Q, but are going to P, okay, but susceptible of species S. Likewise, here I have four indices, L, S, P, Q, okay, likewise. Now, this is in each location a group model, because in each location I can have up to cardinal S species that are interacting. And so the incidence function is much more complicated than the one before, because I now need to sum on all the species that are present in the location. The infection is still, that's the main difference with implicit metapopulations with implicit movement. The infection can only involve species that are present in location P. But all the species that are present in location P can interact with the other species. So this is the rate at which individuals in patch in location P and from species S get infected. Okay? So susceptible individuals from species S in location P get infected at that rate, and that rate depends on how many there are, but on all the other individuals infectious that are located in P. Okay, so that's the sum on K, so that's the sum of all the infectious. So think about plague. Plague, let's suppose plague is easy, or let's think about, for instance, vector-borne disease. If you're looking at a vector-borne disease in a given location, you'll have, let's say, mosquitoes and humans. Suppose I'm looking at malaria. So in each location, I have mosquitoes and humans. Well, my term of infection of humans is going to depend, and so there's no infection from humans to humans in the case of malaria. So I'm going to have, my beta is going to be the number of mosquitoes in this case. Okay. But I describe this with this beta SKP. So in a given location, I will have, if I'm looking at humans and mosquitoes, human to human would be 0, human to mosquito would be a positive quantity, mosquito to human would be a positive quantity, and so on. And you need to sum all of that to get the infection term. Another type of model that I considered with Pulinland and Risha, but originally it was a model from Lisa Sattenspiel and Carl Dietz, is what we call residence travelers models. For instance, I mean, they have a lot of names. Here again, I have two indices, but the two indices are not for species and location, like in the previous model, but for locations. Okay, so this is a p squared, cardinal of p squared model instead of s, cardinal of s, cardinal of p, because here the idea is that the first index represents the location you're from and you're a resident of, okay, and the second index is the location you're currently in. Okay, so this model assumes that you remain at all times a resident of the same location, and it is where you are currently located that changes. Okay, so this allows to track movement of individuals in terms of where they come from and where they are. So, for instance, I've used that to look at models for mass gatherings and so on, because for a mass gathering, people will come from different places. If you think about the models we've seen before, the two models that we've seen before, once you're in the new location, you become a resident of that location for sure. I mean, your movement moves you to a new location and you become a resident of that location. Here, you maintain your location of origin. So if you're thinking about a mass gathering, for example, people will converge from all over the world to a place because of some religious event or some sport event, and then they'll all go home. And when you want to track really what the potential for mixing of these places, these events have, well, you have to tag in terms of where people are coming from. Okay, so here again, you end up in the same type of mechanism as we saw before, where you need to mix everybody that is currently present in whatever location. In terms of the what you can do with that type of model, you can do essentially everything that you're used to seeing with more advanced, more local models. So you can look at all these properties. I'm not going to go over all of them. I'll insist on a few aspects in here, but everything that you know how to do with simpler models in one location, you can essentially do with these. And let me show you this a little bit. So this is the model that I'm going to use. I'm going to take a toy model which has an SIS model, SLIRS model as before. I'm going to assume that infection is this type. And so the result of this is that if I have cardinal of p locations, I have 4 times cardinal of p equations. So if you think about it, that is a lot of equations. For instance, suppose I'm using this for a model of spread between countries in the world. There's about 200 countries in the world. Therefore, I have about 800 equations. But, and this is my point over time when I'm looking at this type of model, the size is not so much of a problem. Because, okay, suppose you're doing the model, you have 800 equations, for instance, but there's a lot of structure in these equations. So you don't have 800 equations. Well, you do have them, but they are not like 800 unrelated equations. They're actually 200 copies of P, we call it of P copies of individual units, each unit having 4 equations. And not only that, typically you understand well the dynamics of the individual units. Furthermore, the coupling is linear. So I have, let's say that I'm doing this world model, I have 200 copies of 4 equations. And on top of that, these equations, where they're coupled linearly. So this is a good case of what we call a large-scale system. This is a very simple case of a large-scale system. And with the matrix analysis that we've already seen, you can resolve this. I'll skip the existence and uniqueness. Who cares? That is not important. Let's just say that it works equally well. So if the model that you're using is a good model, essentially it's well posed, solutions exist and are unique. Typically the model that you put in a metapopulation will have the same properties. Let's look at some properties that you will have to look at typically whenever you look at a model. First one is existence of a disease-free equilibrium. So if I think of a model that's at the disease-free equilibrium, so that's my toy system. Okay, system 16 is the toy model that the SLIRS with a cardinal of p copies. So I'll say that I have a metapopulation disease-free equilibrium if both L and I are 0 in each of the locations. So that's, that's a local equilibrium. So that's in one location. And I have a metapopulation disease-free equilibrium if this is true at every location. So if I want to study what that means, Well, I have to suppose that I have, so suppose I have a metapopulation disease-free equilibrium, then that means that, first of all, there's no transmission. Remember, phi p is the transmission. And furthermore, in each p, for each p uh, location, I must satisfy these two equations. This can look daunting, but it is not at all. Because if you use linear algebra, it goes very quickly. So let me show you how this works. So you take this model, this system, and you write it using a vector form. So these are the same vectors we saw before. Remember, B was the vector of births, D was the diagonal matrix of death rates. I'm actually introducing another diagonal matrix. I'm going to call it nu, and that diagonal matrix is going to be, remember, this is nu is the rate at which you lose immunity, plus the movement matrix for susceptibles. So this is that first equation written in vector form. The second equation written in vector form takes this form. Okay, so this is the sum of two diagonal matrices. It's like this, and this is the movement matrix for recovered individuals. Okay, so I have two vectors, three vectors, S, R, and B, and four square matrices. Well, if you go back to this equation, remember, I'm looking for disease-free, I'm looking for an equilibrium. So I'm wanting to solve this. Well, I play exactly the same game as I played before. I just reorder this, and I see that this is equivalent to finding mr minus nu minus d times r equals to 0. So I'm going to have a unique solution. Okay, this is a homogeneous linear system, so I am going to have a unique solution if and only if this matrix is inverted. That should ring a bell. Okay, so in the previous instance, when we looked at total population without in locations, we had m minus d. Here we have mr minus nu minus d. Well, you can guess what's going to happen. We do the same spectrum shift as we had done before, and we find that in that case, I actually don't need to suppose that all the m's, all the death rates are negative or positive. I just need to suppose that the sum of the loss of immunity and death rates are positive. If they are, then all my eigenvalues have negative real part. Furthermore, I can show exactly the same way as I did last time that all solutions do indeed go to 0 in this case, okay? And so I find that without having to specify that the recovered individuals are 0 at the disease-free, they are indeed 0 at the disease-free equilibrium. Okay? So the disease-free equilibrium has no latent, no infectious, and no recovered, which means that essentially we're back to the previous problem we had looked at. Okay, so I have L, I, and R equal to 0, and now I'm back to this equation here, which is essentially, except that I had an M only before, here I have D minus MS negative, same thing as we've already done. We can easily show that here I need the D's to be positive or irreducibility, but in both cases, I end up with this equilibrium. Okay, so my disease-free equilibrium looks very much like the disease-free equilibrium in single population case, except that, of course, there is a mobility component that plays a role because indeed, as we've seen, the populations can sort of disseminate within the graph. Second part that you might wish to consider is the reproduction number, because that's going to allow you to compute values numerically or look at the local stability, etc. Well, we use the method of Van den Riech and what more in a vector way. So what's important here, and I should point out, I mean, there's some uh, papers that I have written about a variety of things like this. Things get more complicated when you have a more complicated metapopulation model, but in the simple one that we're using here, the order in which we do things is simply we first list the latent compartments and then the infected compartments. If you had, for example, an S, well, if you had a multi-species or a residence traveler model, you'd have to think a little bit about how you order these L's additionally to what we have here. But here we've only got in each location one L. So that's easy. So we first list the L's, then we list the I's, and we say, okay, we use the method of Van den Riech and what more. So we write the dynamics of these infected compartments as so this is psi prime equals to f minus v, where f is a vector, so a column vector, which has the new infections, and v is with a negative sign all the other movements in the compartments. Well, the new infections, they only move into the latent compartments. So that's those cardinal of P components here. There's no new infections going directly into the I compartments. So here we have 0. And V is everything else with a negative sign. So rather than having plus the sums, we have minus the sums of the movements, and the others get the sign is flipped. So these are two vectors with two cardinal of P entries each. Now we differentiate with respect to the infected variables. So when we differentiate the terms, the curly F, which contains new infections, we see that we are looking at the derivative of the infection terms with respect to the latent and then the infected compartments. Okay. So each row is the derivative of one of the terms in the vector with respect to all the infected variables, and so from 1 to cardinal of P. But we note one thing. First of all, whenever, remember it's important, the way the models work is that we assume that infection can only happen in the local locality, okay, location. So I am not infected here by individuals elsewhere. So that means that when I look at the rate of infections, if the indices are not the same, they can only be 0. Okay, because that would be infection in location P by individuals, whether they are latent or infected from location K. Whenever K is not P, those terms have to be 0. So when I look at this matrix that I had here, you can see that what's going to happen is only the diagonal entries are going to be non-zero. Any of, well, a diagonal, this is a block, okay? Think of this matrix as 4 blocks, two blocks here with a phi with respect to L and phi with respect to I, and 2 blocks of 0. Okay, so these 2 blocks can only have the diagonal entries non-zero. Okay, so that means F takes this form. It's a diagonal matrix, another diagonal matrix, and 2 zero matrices. Okay. But not only that, I can look at the two types of force of infection functions that I have chosen, incidence functions that I have chosen. And when I evaluate them at the DFE, the disease-free equilibrium, I see that what I get is that the derivative with respect to latents is 0 in both cases, whether I look at mass action or proportional standard incidence. So the derivative with respect to the L variables is always 0. And depending on what you look at, either it's beta PSP if you're looking at mass action, or beta PSP over NP if you're looking at standard incidence. So that means those two first lines, whenever you're looking at that block of derivatives, that diagonal matrix of derivatives of phi with respect to L, it's always 0. So actually, if you evaluate at the disease-free equilibrium, that matrix, that Jacobian matrix df at the disease-free, which is the F in the matrix in the method of Van den Drieschen what more, well, it simply reduces down to this very simple matrix that has only the diagonal on the 1, 2 block. Everything else is 0. The V matrix you get by differentiating with respect, so differentiating the vector V with respect to the infected variables. And when you compute it, you find this. You find that V is this block lower triangular matrix. Okay, so this is a block of zeros. On the diagonal, you have a diagonal matrix minus the movement matrix for L, and a diagonal matrix minus the movement matrix for I. And here a diagonal matrix again. This is a block lower triangular matrix. Well, it's a 2 by 2 matrix, block 2 by 2, so it's easy to invert. There's a formula for that. But not only is it block 2 by 2, it's block lower triangular 2 by 2, so it's even easier to invert. And so we have a formula for the inverse of a block lower triangular matrix. So it takes this form where this term is a little painful. Okay, it's this term that I have here. You can see that inverse here, but it's computable. Okay, it's not by hand. By hand, it's not feasible, but it is feasible numerically. So now to compute the basic reproduction number, if you're following up on the method of Van den Drieschen what more, we know that the reproduction number is simply the spectral radius of this matrix at the inverse. So we compute at the inverse. Remember, F takes this form, V takes this form. So when I perform this matrix computation, I see that I get a block matrix that has F12 here times V tilde 21, which was that diagonal term that's a bit messy, off diagonal term that was a bit messy, and this term. But this is a block upper triangular matrix. When I look for a spectral radius, the spectral radius, well, the eigenvalues of this is the eigenvalues of this matrix, and the 0 here that comes from this block. Okay, so the spectral radius is going to come from this matrix here. Okay, so the spectral radius of this matrix here is 0, but the spectral radius is here. So it's going to be the max of the two. So we find that R0 is this expression. It's the spectral radius of F12 times this inverse matrix. Okay, so in practice, R0 is this expression that you see here, and the result we have is that, of course, you have to check that the conditions of the Van den Drieschen what more theorem hold, but they hold for the component systems, so they should hold also for, I mean, they hold also here. Okay, but so This is the R0 expression here. You can see it's the spectral radius of this diagonal matrix uh, times the inverse times another diagonal times the inverse. So I will point out that, of course, this is going to be very complicated. Okay, this expression is essentially impossible to compute by hand, even if you have even if you take a very small number of locations, it's going to become very, very quickly difficult. Yeah, something remember that we saw, for example, that if this matrix is irreducible, then that inverse is going to be positive, positive matrix, okay, or a negative. It should be positive here. Which order it works, but it's either positive and positive or negative and negative. But yeah, actually, it is a positive. So that matrix is full. Okay, all its entries here are full, are positive. Here again, same thing. If you have irreducibility, all of the entries of that matrix are positive. So imagine computing this by hand, it's going to be complicated. But if you have numerics, you can compute that very easily. I mean, if you're running numerics, those matrices are going to be easy to compute. It could take a while if you have a very large system, if you have a very large number of locations, but otherwise it's feasible. Okay, so, but given this R0, expression for R0, we then have the natural consequence of this from the theorem of Van Hendrich and what more, is that disease-free equilibrium we found is locally asymptotically stable if this number is less than 1, and it's unstable if this number is larger than 1. One remark, so as I said before, the expression is exact, but it's going to be very complicated to work out. But numerically, unless you have conditioning problems in your matrix, it's going to be very easy to compute. Let me just point out that it's sometimes possible to make the result stronger. So I'm not going to show you this, but it turns out that if we define R0 like before, and we use proportional incidence this way, then R0 less than 1 has the disease-free equilibrium globally asymptotically stable. In the same way, we can do also for the multi-species model with S and P, and we're going to find the same way it's feasible. Okay, so this is all I wanted to say about the mathematics of this. I hope I have conveyed the message that the math is not complicated. It takes a lot of organization, let's say, and but using linear algebra, you get out of this quite easily. One thing that I want to do before I finish on this is talk a little bit about computational considerations, and I'm going to go very quickly, just to show you that essentially the same way as the mathematical analysis is simple. If you use linear algebra, we have the same type of good behavior for the numerics. So what I'm going to do is, again, go very quickly. I'm taking an example here where I'm looking at Canada, China, India, Pakistan, and the Philippines to motivate this. This is China, India, Pakistan, and the Philippines are the four biggest contributors of immigrants to Canada. So this was a model to look at this spread of some disease between these countries. This is the population of the countries, put in million. Um, I make the matrix. This is a matrix that essentially we had some estimates of a number of people that were moving from each country to every other country on a given day. So this is from Canada to Canada, from Canada to China, Canada to India, Canada to Pakistan, and Canada to the Philippines on a given day. Um, I just point out this is a way that you can use to do this. I'll work out the movement matrix. I'm not going to specify how to do that, but you can, incorporating these rates of movement, these number of movements per day and the population, you can compute um, the corresponding rate of movement. So get your matrix M. And you can see here I'm making the matrix M. I'm making the off diagonal entries here. Then I'm setting the diagonal to be 0 because here I'm looping on everything. So I'm setting the diagonal entries to be 0. And then I just make the matrix M because the column sums of M are 0. So I just make the matrix M by putting on the diagonal minus the column sum. Okay, so that gives me column sums equal to 0 with the negative terms, which corresponds to movement out of each country on the diagonal. I set my parameters, so eta is the rate of loss of immunity, epsilon, what model is this? Not sure what model I'm doing. I'm doing an SLIAR. Okay, I'm doing an SLIAR. I can see gamma A and gamma I. But okay, never mind. So this is a little bit more advanced than the model I was showing you before because there's also two types of I and R. I set the desired value for R0. I can also just take random value for beta, but in a sense, I'm just saying in the absence of connection, I want R0 to be 1.5. So if there's no movement, R0 will be 1.5 in each location. So this is where a little bit of cleverness comes in. You can see that what I'm doing here is I'm storing the index indices of the different types of compartments. So this is, and remember, and the same is true for numerics as we've looked at before for the computation of R0, for example. We want things ordered by type of compartment. So I'm saying when I have my vector of states of the system, I'm saying my S are first P, I denoted P, not card P here, the first P locations, then the next P are the L in the locations, then the I, the A, and the R. This allows me to very easily get the vectors, and I'll show you right here. I'll show you later. So this first, I'm setting the initial conditions. These are L, I, A, and R at 0. I'm putting 2 infectious individuals in Canada to start with. I'm setting the initial population to be the population of the initial S0, to be the population in each country, minus my initial conditions. I set my initial conditions. I've showed this in the first term, how to simulate an ODE. This is exactly the same thing. I will need a vector field. I will need initial conditions. I will need a time span. So this is my time span. I'm going to do 5 years. To set the R0, if the patch is isolated, the location is isolated, then I can compute R0 as beta times S0 divided by this. So I can get beta from R0 and these parameters, just like so. And I therefore set the initial the value of beta in each location based on this formula. And this is where the magic happens. It's pretty simple magic. Remember these indices that I set up? When your vector field receives a vector x, in this vector x, I want to, and this is just by convenience. I don't need to do this. It's just, it makes things much simpler. In this vector x, I just say, well, the s variables, they're the first. Remember, these indices were, for s, it was from 1 to p. For L, it was from P plus 1 to 2P, and so on and so forth. And so here, this is simply picking out S, L, I, A, R. And each one of those is a vector with P entries. I compute the total population because I need it to compute the infection. Infection is simply beta times S times I plus eta A divided by N. Okay, because this is a SLIAR model. And then I don't know why there's a backslash here. It shouldn't be backslash. I'll have to correct this. This is simply the movement matrix for the S times matrix times. Okay, it should be just percent star percent times S, and likewise for the others. So you can see that if I were writing an SLIAR S model in a single location, I wouldn't have these terms, but for the rest, it would be exactly the same. You have to be careful when you write this term here that you're, remember with a single star, this is Adama product, entry-wise product, which is convenient here because this is exactly what I want, but you just have to be careful sometimes. But then you return your vector of new values, and you can just run things by doing this. One little trick before I finish. When you're doing the numerics for a system like this, what you will see is that of course, populations are moving. Okay, because independent from the disease, there's going to be some equalization. So depending on what your M matrices are, your system might want to go to a certain equilibrium. Okay. So if you want to consider what happens because of the disease, you want to abstract yourself from this convergence to the demographic equilibrium, essentially. And so to do that, there's a very simple trick that you can play that can be useful sometimes. Put a caveat though, but suppose that I have my endemic equilibrium, my demographic equilibrium, so absent any dynamics due to the disease. Suppose it's given by this. Well, if I want to maintain that the total population in each location is actually like this, what I can do is I can note that if I think in terms of the birth rate, I can write that the birth rate is equal to this. So if I take the birth rate equals to this equilibrium that I want, essentially, then what I do, so not the equilibrium itself, but if I take this d minus m, there's no inverse here, okay? If I take this, then the dynamics of n prime, the total population, is given by this. And that means that by starting at that equilibrium and setting the birth rate to be this value, then your total population in each location remains identically equal to that limit equilibrium that you want. So that means that whatever changes are happening because of a disease, not because your metapopulation is converging to n star. You start at n star, you set the birth rate so that things work, and when you do so, will remain at n star for all times. There's one little problem though. It is that when you do this, it is very likely that you'll find a negative birth rate for some of the components. Okay, so because this is a vector, some of the components in your birth vector might be negative. This is in a way saying that if you want to maintain a certain equilibrium, your population must diminish. Uh, because, for example, if you have a high movement rate from a large location into a smaller location, then that high movement rate will force the population to go up. And therefore, if you want to keep it at a certain level, you have to assume that it's actually dying. Okay. So that would perturb your mathematical analysis, because of course for the mathematical analysis we always suppose that B was positive, or at least non-negative vector, but here you end up with some negative components. But to conduct numerical investigations, this can be a cool trick. And that's it for the lecture about metapopulations.